Okay, so we're going to look at assignment 42, and we're doing problem 39. So again, we're doing rotation. We're looking at conservation of energy. So when we look at the picture, we have this object, and this object is going, so let me just read it. It says the 3-kilogram rod, so this is the rod. So the rod is equal to 3 kilograms. It has a length of 0.8 centimeters. So the length of the rod is 80 centimeters, which I'm going to right away write 0.8 meters. Now, the fact that it is a rod is important because they're telling me it's the rod because I need to then figure out what is the moment of inertia of a rod. Okay, but we'll talk about that in a few minutes because we have to identify something key before we put the I for the rod. The 4-kilogram rectangle attached to the rod, so that rectangle there, the rectangle, the mass is 4 kilograms, is attached to a rod, has negligible dimensions. So the fact that it says it has negligible dimensions, that means when I'm doing the moment of inertia, I'm just going to kind of take it as a point mass. All right. The entire object rotates counterclockwise, so it's going to go like this. Determine the angular speed of the apparatus at the instant the rod is horizontal. So again, this, I didn't really draw that straight. This is my frame of reference. So when the rod then comes down like this, that's what they want us to find omega, and I'll call that omega F. Whenever I have a change of height, like from here to here, even though it's rotating, I'm going to use conservation of energy, because conservation of energy is always the easiest thing to do no matter what when there's a change in height. When I'm doing a problem like this, step number 1 is I need to identify my axis of rotation. So when this does fall, and you might think of it here as the pivot point, where is the axis of rotation? So the axis of rotation is right there. Okay? And that's important because then when I'm looking at things like moment of inertia, again, I'm going to be measuring the distance from like the center of mass of the object to the pivot point. So that's why I always want to identify where is the axis of rotation of my pivot point. So that's important. All right, the first thing I'm going to do is I'm going to calculate my moment of inertia. So for my rod, if I look at it, here's my whole rod. The moment of inertia of the rod to the pivot point is at the end. So because it's at the end, I'm going to look up what is the equation for a rod where the moment of inertia is at the end. Not the middle, not a third, at the end. Okay? So the moment of inertia there is 1/3 ml squared. So it's going to be 1/3 times 3 kilograms times 0.8 meters squared. So when I do all the math, that comes out to be 0.64 kilograms per meter squared. Now I'm going to do the moment of inertia of the rectangle. Now remember, the rectangle has negligible dimensions. So when it has negligible dimensions, I'm just doing the same thing for either a point mass or a system of masses where I'm going to say it's a summation of mr squared, right? So it's going to be the mass, which is 4 kilograms, times the distance to the axis of rotation. So the distance to the axis of rotation is going to be from here to here. So that, again, is going to be 0.8 squared. So this one comes out to be 2.56 kilogram per meter squared. Now there's another step I would do, but I'm going to wait till I need to figure out that step instead of just doing it, because remember, we're working the problem where I'm not just writing answers, we're thinking about what steps you would take if you were doing this by yourself, okay? we're looking at the systematic approach of what would I do next. So now I want to do conservation of energy from here to here. So conservation of energy basically says the total energy before. Here I'm going to have the gravitational potential energy plus the kinetic is equal to the gravitational plus the kinetic. So let's look. So initially, this is this orientation. So initially, I have gravitational potential energy of both the rod and the box. Okay? So I have the gravitational potential energy of the rod plus the gravitational potential energy of the box. Now initially, when it's up here, it's not moving, so the kinetic is 0. Now at the bottom, for conservation of energy, this ground is our frame of reference. Okay? So the potential energy is 0. Both of these would be 0 at the bottom. And then at the bottom, I would have my final will be rotational. Now the trick is this is moving as a system. So when I find the rotational kinetic energy, it's of the combined mass. And we'll talk about that in a second. So let's look here. So this would be the mass of the rod plus gravity plus the height of the rod plus the mass of the box plus gravity times the height of the box is equal to, and the equation for rotational kinetic energy is 1/2 I omega F squared. Now the key here is this this moment of inertia is the moment of inertia of these two things together. Okay? So the moment of inertia, I, this is really I total. So I'm just going to write to the side that the total is equal to I of the rod plus I of the box. So what I would do is I would add those together. So I total would be 3.2 kilogram meters per second. All I did was add these two together. So now let's get back here. So the mass of this is 3 kilograms times 9.8 meters per second squared times, now the rod acts from the center of mass. So the whole height is, remember when this is falling, it's acting from the center of mass, so that would be half of that height would be 0.4 meters plus the mass of the box times gravity times, now the box is the whole height, so that would be 0.8 meters. And that's going to be equal to 1/2 3.2, the total moment of inertia of the system, times omega F squared. Now what I really should have done is I should have rearranged the equation to solve for the unknown in terms of known. And the reason is, so many times on the AP test, they might ask you for stuff. They might say find the angular speed in terms of mgh, you know what I'm saying, in terms of the variable. So we really should get in the habit of doing that because that's a typical thing that they would ask. If you do all the math here, this was like 11.76, this was 31.36, and then when I did the math, omega F came out to be 5.19 radians per second. The key here is you just do it step by step. Again, writing down what you know, thinking about, you want to look at a problem holistically. What's going on with this problem? Oh, there's a change in height. I'm going to use conservation of energy. And then looking at the rod has mass, the rectangle doesn't. Why are they telling me this? There's a reason why they're telling me this. And again, there's essential things you need to write down because when I'm doing this, this is going to be 1 point. This is going to be 1 point. And this is going to be 1 point. And then for some of the other parts, knowing what the moment of inertia is and calculating them for each object. So the point is, when I'm doing this problem, do I want to squish in here this and this together in one line? No, because I'm more likely to make a mistake when I put it all together like that. So go ahead, and I always like to calculate my moment of inertia separate, okay, at the beginning. And normally I would have done the total as well because I knew I was going to do the total, but you didn't, so that's why I didn't do it that way, because we want to look at how would I go about solving this problem if I was doing it on my own. What is my whole train of thought as to step by step to solve this? And that's it.